So our second speaker today is Mathav Murugan, and he will talk about solar spaces and energy measures on the Sierpinski carpet. So please, Mathav.
Thank you very much for the introduction and for this opportunity to speak here. So this is joint work with Ryosuke Shimizu at Waseda University. And I start with an apology that there will be some overlap with my talk from Quasiworld workshop last year in Helsinki. But I try to focus on different aspects of this work to make it as different as possible. Okay. So I'll start with the definition that's hopefully familiar to all of you, which is this notion of conformal gauge. So two metrics are d and theta on some space X are quasi-symmetric if there is some homeomorphism from non-negative reals to itself, such that the ratio of distances between x, y, and xz in one metric can be controlled by a similar ratio in the other metric for all triples of points. And this is somehow the right notion of conformal change of metrics in this context of metric spaces. And this defines what's called as a conformal gauge. So this relation of being quasi-symmetric turns out to be an equivalence relation, and the equivalence class is called the conformal gauge. And there is so this conformal gauge, as Sylvester pointed out in his talk last month, is a huge class of metrics. One would like to pick some metrics that has good properties, and one way to do that is to use this notion of Ahlfors figure conformal dimension, and which is defined to be the infimum over all Q, such that there is some measure mu, which is Q Ahlfors regular, and a metric theta in the conformal gauge, such that this measure mu is Q Ahlfors regular with respect to this metric theta, and we want to minimize Q, and we hope that this infimum is attained, and this gives us some way of picking some good metrics from the conformal gauge. And there are lots of motivations behind doing so that was explained very nicely by Sylvester in last month's talk. One of them is to determine whether or not a Lerner metric exists, for instance. So I'm not going to spend too much time on motivation, but there are various problems that has to do with determining whether or not this infimum is attained. Okay, so this notion was introduced by Burda and Pajo, and almost around the same time by Bonk and Kleiner. And it's a slight variant of Pansu's notion of conformal dimension, where instead of this Ahlfors regularity requirement, we just drop it and asks to minimize over all metrics in the conformal gauge, and we minimize the Hausdorff dimension. Okay, so this definition immediately leads to two questions. First, given a metric space, what's the value of this infimum? And the second question is the infimum attained? And both these questions are open for the Sierpinski carpet, and both these questions are difficult in general. Okay, so the first question I would say is slightly better understood than the second question. And I'll explain what I mean by that soon. Okay, so before going there, I want to mention that, so this definition asks us to find some measure and a metric that satisfies this Ahlfors regularity relation. But it turns out that there is really one of them that we need to pick. The other one is determined by, the metric determines the measure and the measure determines the metric. So this is what I want to explain next. So suppose if you have a metric in the conformal gauge, and mu is some Q Ahlfors regular measure with respect to this metric theta, then the metric theta determines the measure mu in the sense that this measure mu is necessarily comparable to the Q Hausdorff measure. Okay. And conversely, okay, this is a little bit more tricky to see, but this is also well known by now, that the measure mu determines the metric theta, in the sense that if we look at this function, measure of ball of radius dxy with respect to the metric d. So notice that I'm not using this metric theta at all in the right-hand side. So we just define some object that only is determined by the measure mu and this whole metric d, and then we raise it to the power 1 over q, and we essentially look at the largest metric dh such that dh is less than or equal to h, and this can be given by this formula. And this metric dh is going to be Bielefschitz equivalent to the metric theta. So in a sense, up to Bielefschitz equivalence, we can recover the metric theta just from the measure mu. So in a sense, in order to determine whether or not this infimum is attained, we can either try to find the optimal measures or the optimal metrics, and one of them determines the other. So in this talk, the viewpoint will be to try to find the optimal measures and use that to hopefully find the optimal metrics. Any questions so far? Okay, so let me talk about Sierpinski carpet, which is again a familiar object. So we have a unit square, and I have labeled the 4 corners and the 4 midpoints from 1 to 8 in the counterclockwise direction. And we have these 8 contraction maps, which are all contractions by a factor of 1/3, centered at these 8 points. And Sierpinski carpet is the unique non-empty compact subset such that this carpet is the union of these images of K under the 8 contraction maps. Okay, and we restrict this contraction map to the carpet and call this capital Fi for each I from 1 to 8. And we can compose these contractions. Suppose we have a word of length n in this alphabet that's made of numbers from 1 to 8, then FW is the composition of these n contraction maps. So each contraction contracts by a factor of 1/3. So FW will contract by a factor of 3 to the n. And the image of the Sierpinski carpet under the contraction is denoted by KW. Okay. And then so this, we will view the Sierpinski carpet. We will view the Sierpinski carpet as limit of graphs for in this talk. So there is a notion of graph approximations of the Sierpinski carpet, which is natural given these contraction maps. So the graph approximation at level n, this graph is denoted by Gn, whose vertex set is Vn and the edge set is En. Vn is simply S to the n. So these are words of length n in the alphabet 1 to 8. So, and we have an edge between 2 vertices if and only if their corresponding images under the contraction map are non-empty. So the picture for n equal to 1 and n equal to 2 are given here. And then I'm going to denote some special subsets of vertices. So these are Tn and Bn. So Tn, so remember so 1, 2, 3 are the vertices on the bottom line, and 5, 6, 7 are the vertices on the top line. So if you look at 5, 6, 7 and then raise it to the power n, these are all the vertices that are touching the top, whose images under the contraction map are intersecting the top line of the carpet. And similarly for the bottom line, we have this 1, 2, 3 raised to the power n. So you can think of this as the top and bottom boundaries of the carpet. Okay. So remember, I started this talk with 2 questions about conformal dimension. What's the value and when it's attained? So I'll describe the answer to the first question, the value of the Ahlfors regular conformal dimension. So we have this graph that I just described, and we can look at the discrete energies, which is simply the P energy where you define, look at the difference between the function at two neighboring vertices. So this is some kind of discrete gradient and raise it to the power p and sum over all edges. And so Buddha and Kleiner show this result. So for any p between 1 and infinity, there exists some constant and some exponent rho p, which is positive, such that if we minimize the p energy, the discrete p energy over all functions, such that the function is 1 on the top and 0 on the bottom, then this minimization, this minimum energy grows like some exponent raised to the power minus n. Okay. So this just for convention, I can even choose plus n by just taking reciprocals, but this is going to be convenient for later on. And there is an unpublished work of Keith and Kleiner. There is also a work that describes this proof of Carrasco that states that the Ahlfors regular conformal dimension is precisely the smallest value of p for which, well, it's the infimum over all p larger than 1 such that rho p is larger than 1. Turns out that there is only one value of p where rho p equal to 1. That's the Ahlfors regular conformal dimension. Yeah. So this tells us that, okay, so we can look at these discrete energies and by looking at some kind of critical exponent that's associated with the discrete energies, one can determine what the Ahlfors regular conformal dimension is, at least in principle. It's actually not so easy to explicitly calculate these numbers rho p. So we only have some numerical simulations that give some range of values of rho p. We do not know its exact value, but still at least we have a good understanding of what rho p should be by looking at these discrete capacity or modulus problems. Okay, so since we can use discrete energies to understand the answer to the first question, which is the value of the Ahlfors regular conformal dimension, it's natural to try and use discrete energies to understand the second question, which is whether or not the Ahlfors regular conformal dimension is attained. So that's kind of the motivation behind this paper. So trying to see if discrete energies can also say something about the attainment problem. Okay, so this theorem of Buddha and Kleiner suggests us to look at rescale discrete energies. So if you rescale the discrete energies by rho p raised to the power n, then hopefully that kind of rescale discrete energies converges to some non-trivial object. And that's exactly what we do. And this is also something that was done in the case p equal to 2 by Kusok and Zhou to construct Brownian motion on the Sierpinski carpet. So I'll describe this rescaling procedure. So here we equip the Sierpinski carpet with the Euclidean metric D and the self-similar probability measure M, such that each rescale copy at level n, so there are 8 to the power n rescale copies. Each of them are assigned equal measure, which is 8 to the power minus n. And for any integrable function with respect to the self-similar measure, we can approximate it on the graph by defining the approximation on the graph as just the average of this function on the corresponding copy of the corresponding rescale copy of the carpet. So what we can show is the following. So this is, this is a result that we call as weak monotonicity. So the rescale energies behaves almost like a non-decreasing sequence in n. So we look at any function f in LP, and we look at we discretize the function using this procedure, using this averaging procedure, and we compute the discrete energy. So that's this term, E, M, and F. And then we rescale by this factor rho p raised to the power n, that's suggested by this theorem of Buddha and Kleiner. and once we do that, as n increases, this function is almost non-decreasing. More precisely, what we can show is that the supremum overall n is less than or equal to constant times lim_inf. So in particular, the lim_inf and lim_sup are going to be comparable. We do not know if the limit exists, but at least we know that at least passing through a subsequence, we should get a decent limit. And the limit might depend on which subsequence you choose, but only up to a constant factor.
Excuse me, Mathav,
Yeah.
just a side question here. So, right, I mean, this formulation makes reference to this choice of the reference measure, the background measure M.
That's right.
A clean way to state this that doesn't use such a choice, because I mean, you could replace that with some other measure, right?
That's right. Yeah. So this reference measure is, in sense that this is not a good measure, right? Because you want to choose maybe some other doubling measure, which is maybe closer to the optimal measure. The answer is, well, so we do not. So that's part of the problem, right? We are trying to find a good measure. So if we change this measure M to some other doubling measure, which is, let's say, a probability measure, then the resulting space could be different. I'm not. I don't think it will be the same.
You could replace M with another I mean, natural class of measures to look at first will be just all doubling measures, right? And then
then I'm not sure how to show this weak monotonicity. It's possible that it's still true, but there might be some restrictions on the measure. So the way we prove this kind of weak monotonicity statement is to first prove Poincare inequalities which are uniform for discrete approximations. So these Poincare inequalities allow us to compare small scales with large scales, and it's easy to do it for it's not that easy, but it can be done for the uniform measure, but with weights, it's not so clear how to carry out that argument. But on the other hand, I believe that when P is exactly equal to the Ahlfors regular conformal dimension, no matter which doubling measure we choose, we should essentially get the same space. And this is somehow related to this conformal invariance of Dirichlet energy when P equal to the Ahlfors regular conformal dimension.
This is sort of an enhanced statement because it holds for all P, right?
Yeah, that's right. This is for all P, but but for applications to the attainment problem, the only P that matters is when P equal to the Ahlfors regular conformal dimension. And from so from that viewpoint, it shouldn't matter which measure we choose.
But so then what's your using self-sim? Oh, sorry, go ahead, Mario.
Okay, the only thing I wanted to add was, but if P is different, there is no reason to expect that changing the measure would lead to similar energies or the similar kind of Sobolev spaces. Okay.
Thanks.
Okay, so this is an important fact about these discrete energies or rescale discrete energies that's used to construct the Sobolev space. And here is the main theorem about the Sobolev space and the corresponding energies. So we just look at the rescale energies, and we can either take supremum or lim_sup or lim_inf. They're all going to be comparable. We just chose supremum because the triangle inequality for this seminorm would be obvious. And we can define this non-homogeneous Sobolev norm, which is the sum of the LP norm plus the sum of this seminorm that comes from looking at rescale discrete energies. And we can define the Sobolev space as all functions in LP such that this rescale discrete energies supremum is also finite. And this leads to a nice reflexive separable Banach space. And it turns out that the continuous functions in this space are dense in two different ways. First, it's dense in the Sobolev space with respect to this norm. And also it's dense in the space of continuous functions with respect to the uniform norm. So there are lots of continuous functions. And then, so this supremum is not a nice choice because it's not clear that this kind of object is a local object. So it's more, it would be nicer if we can take some limits as n goes to infinity instead of looking at supremum. And we do that, but only along some subsequence using this theory of gamma convergence, we can show that at least along some subsequence, we can get a nice energy. So there exists some C, and this nice energy is called EP, which is basically like a P energy, which is the integral of absolute value of gradient of f raised to the power P. And this is going to be comparable to the supremum. This is because of what I said before, the sup and lim, inf and lim sup, they're all comparable to each other. And it satisfies a nice self-similarity property. So for any function in the Sobolev space, if we compose f with one of these contractions, so we are just restricting the function to one of these 8 copies, then this new function is also going to be in the Sobolev space. And the sum of the energies of these 8 copies rescaled by this factor rho p, which is the same rho p that we saw in this Bourdon-Kleiner result, is going to be the energy of the function. And furthermore, the domain itself also has this self-similarity property in the sense that if you restrict the set of continuous functions in the domain, these are precisely all those continuous functions such that the restriction to each of these 8 copies are in the Sobolev space. And we can also construct these energy measures, which are formally thought of as the energy measure of a function f. Maybe in the classical setting, you should think of it as the measure that assigns to a set A the integral over A absolute value of gradient of f raised to the power p. So that's the p energy measure, and we construct an object similar to that. So for any function, the integral over the whole space should be same as this p energy that we constructed, and any of the copies, it's going to be same as rho p raised to the power n EP f of the function that's blown up to that copy. And this statement is, it's not as simple as it seems. Actually, to prove that statement, we need to show that the intersection between any two cells should have energy measure 0 for any function in the Sobolev space. And we were able to show that. And it also satisfies a chain rule, which should be natural for any functions which is continuous in our Sobolev space, and for any C1 function, the composition of C composed with F is also going to be in our Sobolev space, and the energy measure of such a composition satisfies this chain rule, which is known in the classical setting of Sobolev space and Euclidean space, but can also prove it in this setting. So these are all true for any values of P. But from now on, I'm going to focus on the case when P equal to Ahlfors regular conformal dimension, because that's the most relevant space for this conformal dimension problem and the attainment of conformal dimension. Okay. Before I go on, are there any other questions? Okay, so maybe some remarks on this proof. So similar result was shown by my co-author Shimizu and also by Kigami when P is larger than Ahlfors regular conformal dimension. Kigami did not construct the energy measures, but Shimizu did construct the energy measures. Also, Kigami's framework is more general, but Shimizu just does Sierpinski carpet. Okay. And there is a result of Chao, Chen, and Kumagai that shows that the Sobolev space contains discontinuous functions if and only if P is less than or equal to the Ahlfors regular conformal dimension. This is natural from this result of Keith and Kleiner and Carrasco that I mentioned earlier, because because this Ahlfors regular conformal dimension can be viewed as some kind of critical exponent for discrete energies. And since we are constructing the Sobolev space from discrete energies, there is this transition. One can build this continuous function in the Sobolev space if P is small enough. And the main difficulty in proving this kind of result was to prove Poincare inequality, which is uniform in N for this discrete sequence of approximations. For that, we used some old ideas of Bonk and Kleiner. Using this estimates, Bourdon-Kleiner estimates for modulus, one can show that the capacity between balls have good lower bounds, but we can upgrade from capacity between balls to capacity between curves using this Bonk-Kleiner argument. And then one can upgrade lower bounds of capacity between curves to Poincare inequality using another argument of Heron and Koskela. So we can do this all, this is all done in a different setting, but the same ideas also apply in this discrete setting as well. And many of these arguments were only done in the case, and in fact, both of these arguments were only done in the case P equal to Ahlfors regular conformal dimension. But it turns out that this argument also works when P is a little bit less than Ahlfors regular conformal dimension. I think the best one can get out of this argument is something like P is larger than Ahlfors regular conformal dimension -1, something like that. That's the range of P in which it works. But fortunately, since the Ahlfors regular conformal dimension is less than 2, this arguments work for all P larger than 1. But for very high dimensional spaces, there is no reason to expect these arguments to work for all P larger than 1. And then the proof of regularity, which is this density of continuous functions, relies on obtaining some discrete version of Harnack inequalities for discrete version of p-harmonic functions on these approximations. Okay, so now I'm going to talk about a more classical version of Sobolev space, which is well known in this community, but I'll quickly remind. This notion of Sobolev spaces that comes from upper gradient. This is you have this metric measure space, and for any function, you can define what's called as an upper gradient, which is that for any rectifiable curve gamma on the space, the function, the difference in the function between these two endpoints can be controlled by this integral of the upper gradient on this curve over this arc length measure. And we say that it's a p-weak upper gradient. So the notion of upper gradient is not nice from a function analysis viewpoint because it's not closed under taking limits. So in order to close it, we need to introduce this weaker notion called the weak upper gradient. So we said that G is a p-weak upper gradient if there exists some non-increasing sequence of upper gradients which converge to this limit G in the LP sense. So this is some analog of this inequality G is less than or equal to, sorry, I think it should be G greater than or equal to absolute value of gradient of U, because if a function is an upper gradient, any larger function is still going to be an upper gradient. So this is a typo here. And we can try to find the smallest one, which is in principle should be equal to the length of the gradient vector. And the smallest, it turns out that if U has a p integrable upper gradient, then there is a unique smallest one, which we call it as GU. This is the minimal p-weak upper gradient. And this is an analog of the length of the gradient. And so using this minimal p-weak upper gradients, one can define Sobolev spaces, and this was introduced by Chiger, and in a slightly different formulation by Shanmugam. And this requires, okay, so first we define this as the set of all p integrable functions with a p integrable p-weak upper gradient. So in that case, we know that there's a minimal p-weak upper gradient, and we can define a norm, in fact, a semi-norm by looking at the function, LP norm of the function plus LP norm of this minimal PV upper gradient. And we do the usual thing in function analysis to define a norm from a semi-norm, which is to just take quotients. Two functions are said to be equivalent if the difference has this semi-norm equal to 0, and this quotient space is going to be a norm-linear space, and it's a Banach space. It's this Newton-Sobolev space. So this procedure, if you do it for the usual Sierpinski carpet with the Euclidean metric and the Hausdorff measure that I described before, this is just going to lead to the LP space, because it turns out that the minimal PV upper gradient for any function in LP is 0. So this is a problem, and this is kind of why we had to come up with a definition of Sobolev space that doesn't rely on upper gradients. Okay, so I want to connect this Sobolev space that comes from upper gradients to the Sobolev space that comes from discrete energies, and so I'll do that next few slides. So here is the main application to the attainment problem. So from now on, P is always going to be equal to the Ahlfors regular conformal dimension, and theta is some metric in the conformal gauge such that the measure is P Ahlfors regular. So here I'm assuming that the attainment happens. Then there is some function or Sobolev space H, which is in FP. So I have emphasized I have written FP as FP KDM to emphasize the fact that this Sobolev space comes from looking at Euclidean metric and the usual Hausdorff measure with respect to the Euclidean metric, such that any optimal measure is comparable to the energy measure of some function in our Sobolev space. So in particular, we might as well replace mu with this energy measure of this function. So energy measure is going to be an optimal measure for this attainment problem. So this is kind of the main message. Optimal measures are necessarily energy measures up to a bounded perturbation. I mean, so it's already known that any two optimal measures should be mutually absolutely continuous with respect to each other. This follows from a result of Heron and Koskela. In fact, they show something stronger. They are going to be A infinity related. And if an optimal measure exists, then it must necessarily be singular with respect to the Hausdorff measure. This is an unpublished work of Kleiner, but we include this argument in our paper with its permission of Bruce. So this this reason is this is quite interesting, because this measure is going to be very different from the usual Hausdorff measure, and this is maybe one of the motivations to study energy measures, and this also tells us that these discrete energies are not only important for the value of the Ahlfors regular conformal dimension, but it's also important to determine whether or not it's attained. So hopefully this leads to more interest in energy measures of functions. Okay, so I want to give some ingredients behind the proof of this result. So the proof, okay, so here is some piece of notation. P is going to be the Ahlfors regular conformal dimension, and Q is the usual Hausdorff dimension. So proof involves 4 kinds of point-grain inequalities. So I'll start with the first one. The first one is kind of known. It's known that if the attainment happens, if theta is in the conformal gauge and mu is optimal for the Ahlfors regular conformal dimension, then K theta mu is going to be what's called as a Launer space. In particular, it satisfies a 1p point-grain inequality. Okay, so the 1p point-grain inequality, this is defined for this Newton-Sobolev space that I just talked about. So here is how it goes. So that there exists some constant C and A, such that for any function, this Newton-Sobolev space, and for any ball of radius r centered at x, we have this kind of p variance is controlled by r to the power p times the integral of gf, the minimal PV Kappa gradient of f raised to the power p on a slightly larger ball. In fact, this a can be chosen to be 1 if we are willing to change theta up to a Bi-Lipschitz factor to make it geodesic. Okay, so that's the first kind of point inequality. So this point inequality can be thought of as a point inequality for this optimal geometry k theta mu. The next point inequality is going to be a point inequality for the Euclidean type geometry KDM, and this comes from these discrete point inequalities on graphs and taking limits of those. So this is how it's stated. So this is for any function in the Sobolev space FP that comes from the Euclidean geometry by looking at these rescaled discrete energies. So here we have a p variance, but now the p variance is with respect to this measure m that comes from Euclidean geometry. So this is the Hausdorff measure, and on the right hand side we have something like the integral of the it's just the p energy of the function that comes from discrete energies on a slightly larger ball. This is all with respect to the Euclidean metric and this Euclidean type Hausdorff measure. But here on the right hand side, if we compare it to the previous point inequality, instead of r to the power p, we have r to the power q, where q is the Hausdorff dimension instead of the Ahlfors rather conformal dimension. So that's the second one. So these two are kind of point inequalities that are about these two different geometries, one from the Euclidean side and the other from the optimal or the Launer type geometries. And there are two other point inequalities which are really you can think of them as mixed type point inequalities. They somehow relate these two spaces. So on maybe I'm going to talk about the first mixed type. So here we are going to look at functions which are in this N1P Sobolev space for the optimal geometry, which are continuous. And it's enough to restrict to continuous functions because continuous functions are dense in both this Sobolev space for the N1P Sobolev space and also for Sobolev space that comes from discrete energies. So here, the first one states the following. So here we are looking at the p variance with respect to the measure m, which comes from the Euclidean Hausdorff measure. So it seems we are doing something wrong here because the function f is on the Sobolev space that comes from the optimal attaining metric and measure. But here we are looking at the variance with respect to the Euclidean one. In fact, this is why we have to restrict to continuous functions, because these functions N1P is defined on a measure mu, which is singular with respect to this measure m. So, it doesn't make sense to talk about these integrals unless we restrict to continuous functions. And then on the right hand, yeah.
But a small point here. Since you use N1P functions, they're actually defined pointwise at every point. So you could use, and in this case also the Sobolev functions have a precise representative that is defined at capacity almost every point.
Right, but we do not. Yeah, but we do not know that the capacity. It should be true, but we do not know if the capacity almost every point is well defined up to m almost every point.
Yeah, if you are when you're Loevner, and if you take any doubling measure, then you are defined mu almost everywhere. Because
that's right.
But
mu and m are singular, right?
Yeah.
Yes. But mu and m are singular.
So if you have a Q Ahlfors regular Q Loevner, and you take any doubling measure, then with respect to that measure, you're defined almost everywhere.
Okay, I see. Okay.
So even with the original,
I see.
You have like Lebesgue points outside of a Q capacity set, but it's almost a Hausdorff zero-dimensional set.
Okay, I did not know that. Okay, then
it has Hausdorff dimension less than epsilon for any positive epsilon, and any doubling measure will then not charge those sets.
Yeah, I mean, it seems reasonable. I thought something like that should be true, but I did not know that it was already known. But, okay, yeah, good.
I
But
think
in any
these,
case,
like in the continuous world, these are actually called like trace Poincare inequalities. So these types of where if on the left-hand side you have a singular measure. So I mean, they are at least Shanmugam, and they have a number of these results that if your measure has some codimension bound, then you have a version of a Poincare inequality in a trace result.
Right, but here we are not restricting ourselves to some smaller subset, right? We are talking about the whole space.
Absolutely, yes. But so these trace results are also for other generally measures.
I see.
So I think some of the results are also stated for general measures, but then they're generalizations of the case where they happen to be supported on lower dimensional sets. But anyway,
yeah, I have seen this kind of Poincare inequalities also called as two-weight Poincare inequalities, because there is this measure m and there is this measure mu, but often in that two-weight Poincare inequalities, m has some density with respect to mu, but here it's actually singular. But yeah, so yeah, I think these kind of Poincare inequalities exist in the literature. Okay, so here on the left-hand side, we have this measure m, and on the right-hand side, we have this energy that comes from the optimal Launer type space, while on the left-hand side, we have variance that comes from the Euclidean space. And the next Poincare inequality does exactly the opposite. Left-hand side, we have variance that comes from the Launer type space, and the right-hand side, the energy that comes from the Euclidean space. So these inequalities are very important in comparing these two energy measures. So this, for example, already contains a lower bound on the energy measures for the Launer space using some kind of variance that comes from the Euclidean space, and the other way around here. And one can also prove similar upper bounds, and this allows us to compare the energy measures that comes from the minimal PV upper gradient for the optimal attaining metrics and measures, and the energy measures that comes from these rescaled discrete energies. Okay, so here is the result that compares these discrete energies and energy measures. So here again we have P equal to the Ahlfors conformal dimension, and theta is as before is the optimal is an optimal metric, and mu is an optimal measure that attains the Ahlfors conformal dimension. Then we can show that these two spaces are indeed the same with comparable norms, semi-norms, and energy measures. So I have to explain this more precisely. The space of continuous functions is exactly the same in both these spaces. And so these equivalence classes are slightly different because this comes from looking at equivalence relation with respect to the LP space for M, and this comes from looking at equivalence relation for this N1P. Maybe from what Sylvester just told us, maybe these equivalence classes are not as different as they seem. But at least one can extend this bijection between continuous functions as a linear function uniquely to the whole Sobolev space from one Sobolev space to the other, such that this bijection preserves the energy measure up to a multiplicative constant. And also, so if you take the energy measure of the whole space, it also preserves the energy up to a multiplicative constant. But what's surprising is that it not only preserves this energy, which is this homogeneous energy, but also preserves the non-homogeneous energy up to a multiplicative constant, which is what, this is the norm that comes from looking at the energy plus the LP norm. And from this result of Bruce that I mentioned earlier, that this measure mu is going to be singular to M, the LP norms themselves are not going to be comparable. because of the singularity. But on the other hand, if you add energies, it's going to be comparable. Okay, so and once we have such a result, it's easy to prove the result that I mentioned before, that if you have some optimal measure, then this measure is comparable to the energy measure of some function in the Sobolev space. Here is how the proof goes. So one can replace theta with some Bi-Lipschitz equivalent metric that's actually geodesic. That's well known because it's a Launer space. And then one can just look at the function which is distance with respect to the metric theta from some base point in the space. And it's known that such a metric should have a minimal upper gradient 1 almost everywhere. So the energy measure for such a function is just going to be 1. And since it's also continuous, that function should also belong to the Sobolev space that comes from the energy measures. And as a result, this should also come from such a function should also belong to the Sobolev space that comes from discrete energies, and the energy measure should be comparable to this measure mu. So that's one way to see this. So once we have this kind of comparability between energy measures, it's very easy to show that any optimal measure is necessarily a bounded perturbation of energy measures that comes from this discrete Sobolev space. Okay, so and it turns out that these optimal measures are what's known as minimal energy dominant measures. Here's the definition. So this definition was first introduced in this theory of Dirichlet forms, but the definition is the following. So we have this this energy EP and the corresponding Sobolev space FP. So it satisfies these two properties. It satisfies the domination property, which means that for every function in this Sobolev space, the energy measure is going to be absolutely continuous with respect to this measure mu. And it satisfies the minimality property in the sense that if there is some other Borel measure nu prime that satisfies the domination property, then this nu prime should dominate the minimal one. So these measures are determined up to mutual absolute continuity of measures, and we can also show that any measure that's optimal for the attainment problem is a minimal energy dominant measure for this Sobolev space that we construct. So this has an interesting consequence. I want to mention this consequence in order to relate to the talk of Sylvester and Riku from last month. So in particular, if Ahlfors regular conformal dimension is attained, then for any function in the Sobolev space and for any porous subset of the space, the energy measure should be 0. This is just from Lebesgue differentiation. And actually, we do not know whether this property is true or not for our Sobolev space. But suppose if we can show that this property fails for some function, then we immediately can show that the attainment doesn't happen for carpet. So the reason why I mentioned this is because of the discussion on porous subsets by Sylvester and Riku last month. So I think what should be true. So I started this talk with two questions. So one is the value problem, value of Ahlfors regular conformal dimension. The other is the attainment problem. So for the value of the Ahlfors regular conformal dimension, there is this very nice result of Keith, Kleiner, and Carrasco that tells us exactly what it should be based on this critical exponent of energies. That's a very general result. Even though I just stated it for carpet, it's known for a very general class of metric space. Basically, it's as general as it can be. But our result, on the other hand, is very specific to carpet. So it would be nice to have a similar result of level of generality for the attainment problem as well. So we believe that energy measures should be relevant for attainment problem for other self-similar spaces as well. So one should try to construct energy measures and Sobolev space on other fractals. In particular, we conjecture that the optimal measures are necessarily minimal energy dominant measures for Sobolev spaces that are constructed using discrete energies. So this should be true at the same, more or less at the same level of generality as this result of Keith and Kleiner and Carrasco. I mean, that at least that's the conjecture, and we would need to understand energy measures better in order to solve these attainment problems. That seems to be very difficult because it's defined, often using the subsequential limits and things like that. It's not easy to get some concrete estimates. Okay, so this point I already mentioned. So the theorem of Keith and Kleiner and Carrasco are very general, but our result is much more restricted. So one would like to aim for a similar level of generality for the result that connects the attainment problem to discrete energies. Okay, so and finally, I want to say a little bit more about the relationship between this work of Riku and Sylvester. So what to expect? I mean, this is kind of possible scenarios that I could come up with. So that could be a function, the Sobolev space, whose energy measure is concentrated on a porous subset. So this is, as I explained earlier, this is a sufficient condition for non-attainment. I think this scenario should happen, and for the counterexample, Kleiner's conjecture discussed by Riku and Sylvester last month. The way the proof works, it's clear that if one tries to construct Sobolev spaces, and if this conjecture was true about minimal energy dominant measures, optimal measures being minimal energy dominant, then this kind of energy measure approach should also provide another proof of the same result. And it could be possible that there are functions in the Sobolev space that has very nice energy measures in the sense that they're doubling. But it could be possible that if we try to construct the metric using this David-Sims procedure that I explained at the beginning of the talk, these metrics need not be in the conformal gauge. This could also be a way of non-attainment happening. This is a little bit more subtle than the first scenario, but this could happen. Naotaka, Kajino, and I have worked on a related attainment problem for a different kind of conformal dimension called the conformal walk dimension, where this phenomenon actually does happen. And maybe the third one is the most optimistic scenario where attainment happens, but it's also, I think, the hardest to check. So here, there might be a good function, the Sobolev space, such that the energy measure is doubling and the corresponding David-Sims metric is actually in the conformal gauge. So we have attainment. But the problem is that it's very hard to get enough good estimates about the energy measure in order to say something about the corresponding David-Sims metric. And for example, one could even hope that if you look at the p-harmonic measure, that's 1 on the top line and 0 on the bottom line, and harmonic everywhere else, there is definitely such a function in our Sobolev space. It might even be possible that the energy measure of that function is already an optimal measure for the attainment problem, but we cannot obtain any precise estimates for that Sobolev space for those kind of functions in order to conclude something definitive. I thank you very much for your attention. That's the end of my talk.
Thanks, Mathav, for your talk. So, comments or questions?
Question, Mathav, I'm trying to remember. There's some general nonsense classification of radon measures. They have a sigma porous piece. They have a pointwise doubling piece. Or I'm sure somebody here knows the statement. I'm kind of fuzzy on what it is. But so if an energy measure has a piece that's not asymptotically doubling, can you use that to get non-attainment? So you're saying it's entirely, in one of the cases, it's like entirely sigma porous and with no asymptotically doubling piece, right?
Yeah, that's right. So suppose the attainment happens, then we know that the energy measure of any function is going to be absolutely continuous with respect to this doubling measure, which implies that the energy measure of any function in the Sobolev space should be asymptotically doubling. So if the asymptotically doubling property fails for some function in the Sobolev space, that's already a certificate for non-attainment.
So what can you say about the structure, just a priori, putting aside the question of attainment? Can you say about the? I mean, I guess two questions. Do you get quasi-symmetry invariance, full quasi-symmetry invariance?
We didn't work in that direction, but I think when P equal to the Ahlfors regular conformal dimension, it's conceivable that there is some quasi-symmetry invariance. So we maybe instead of discretizing using the Euclidean metric, we can start with some other metric in the conformal gauge, discretize using that metric, and instead of using the Hausdorff measure to define these energies, one can also look at some other doubling measure to define the discretizations. And I believe that when P equal to the Ahlfors regular conformal dimension, this Sobolev space and possibly the energies and energy measures are uniquely determined up to up to bounded perturbations or something like that. I think that's very reasonable to expect to be true, but we didn't work in that direction at all.
Oh, well, one point in that direction, right? So it should be possible when P equals to the conformal dimension, it should be possible to identify the Sobolev space with the other Sobolev spaces that already appeared. For example, the one that Mario and Aero worked on. I think they should be the same, and they already have the quasi-symmetry invariance for that Sobolev space. So then that would be a sort of a free way of getting it. And also for P equal not, or go ahead, Mario.
Yeah, right. I was going to ask this, right? I mean, in this paper with Aero Saxman, I mean, we somewhat tried to define these Sobolev spaces just based on the notion of hyperbolic filling, without any reference to some underlying measure. So it would be very interesting to see, what the connection is.
No. I thought in your paper with Aero, you try to discretize the function, right? You have a function on the boundary, and then you try to define some function inside the filling, and you need some measure to average things.
Well, I mean, there are two directions, right? I mean, if you have a function on the boundary, then you can do some kind of averaging procedure. But conversely, you can somehow start with a function on the hyperbolic filling, and then get some kind of trace on the boundary.
I see.
So it's very similar to this Baudon-Pajot paper where they worked in this El-Pico homology, right? I mean, you can always start from the boundary, go back to the filling, or conversely, just have something on the filling and then get some kind of a trace on the boundary. And you can completely start in this direction, right? I mean, you have something on the hyperbolic filling, and then you get some kind of a natural space on the boundary as the space of traces of these functions.
Yeah.
Yeah, and this shouldn't be too sensitive to how this one goes from the boundary back into the space. I think there should be some flexibility there. But I think Mario will have to soon run out. But I wanted to quickly ask, this relates to your third point there about looking at particular functions. Can you say that this, or do you expect that it's enough to look at, say, harmonic Sobolev functions?
Yeah. I mean,
with some kind of blow-up argument, because these functions should be asymptotically harmonic.
Right. I mean, there is this, in Chiga's paper on this Rademacher's theorem, he has this nice argument where, if you blow up any function at almost every point, the result is going to be harmonic or something, or generalized linear. I forgot what the terminology is.
Shouldn't the same argument work with energy measure almost every blow up?
No. But the point is, we do not know whether there is a doubling measure that's minimal energy dominant. I think there are some abstractions like that. In fact, for this other problem of conformal walk dimension, we were able to show some similar statement. But here also, I believe something similar should be true. But the proof there fails when P is not equal to 2 because of, at some point we use the fact that the difference between two harmonic functions is harmonic, but that's no longer true in the nonlinear P Laplacian setting.
Yeah, but this might be,
sorry.
This issue might be a bit similar to, well, one thing is that they're not asymptotically doubling, but that might not preclude taking blowups. I mean, if you have a measure supported on a hyperplane, that's not a doubling measure supported on a hyperplane. It's not doubling in Rn, but you can still blow it up. And there's this, maybe what could be helpful is actually doing some kind of weaker blow-up procedure like what is done in GMT, where you prove that at almost every point there exists some sequence of blowups that give you.
I think one can do blowups to get some measures. That should not be an issue, but what we would ideally like to say is the following. We can blow up measures, you can also blow up functions. We want to say that this blown up measure is the energy measure of the blown up function. To identify them seems to be the tricky part. Just doing one of them is not difficult.
Yeah, but your energy measure is so similar, so that might be very helpful there. Yeah.